The Second World War witnessed unprecedented technical ambition in aviation, and among the most radical developments were aircraft powered not by propellers, but by rockets. They promised extraordinary speed and climb rates that piston engines could never achieve, yet brought extreme risk, limited endurance, and immense technical complexity. Between 1939 and 1945, engineers in Germany, Japan, the Soviet Union, and the United States raced to harness rocket propulsion for military purposes. This is the complete record of every rocket-powered aircraft tested during the Second World War. German rocket aircraft. Germany led the world in operational rocket-powered flight during the war. Desperation for air superiority and access to advanced chemical propulsion technology drove an aggressive development program that produced the most sophisticated designs of the era. The Messerschmitt Me-163 Komet stands as the only rocket-powered interceptor to see widespread combat use. Development began in 1938 under Alexander Lippisch, building on his experience with tailless glider designs. The aircraft used a Walter HWK-109-509 rocket motor, burning a volatile mixture of T-Stoff and C-Stoff. This combination was hypergolic, igniting on contact, and extraordinarily dangerous to ground crews. The Komet entered service in mid-1944 with Jagdgeschwader 400. Its performance was staggering. The aircraft could reach altitudes of 12,000 meters in under 3 minutes. Maximum speed exceeded 960 kilometers per hour, making it the fastest operational aircraft of the war. Allied bomber crews had almost no time to react during attack runs. Yet the Me-163 suffered from crippling limitations. Powered endurance lasted only 7.5 minutes. Pilots had to climb, locate the target, attack in a single high-speed pass, and glide back unpowered. The landing approach was particularly hazardous. The aircraft landed on a retractable skid, and any remaining fuel could explode on impact. Dozens of pilots died in landing accidents. Combat effectiveness proved disappointing. The closure rate during attack runs was so extreme that accurate gunnery became nearly impossible. The two 30mm cannons had only seconds to fire before the Komet overshot its target. Pilots scored fewer than 20 confirmed kills against hundreds of sorties. The Me-163 remained a spectacular failure despite its revolutionary design. The Bachem BA-349 Natter represented an even more radical concept. This was a vertical launch interceptor designed for semi-expendable use. The pilot would launch from a vertical rail, climb under rocket power, fire unguided rockets at bomber formations, then bail out. The engine section would descend by parachute for recovery and reuse. Development occurred late in the war under extreme resource constraints. The BA-349 used a Walter HWK-109-509 main engine, supplemented by 4 solid-fuel boosters for launch. The entire fuselage was constructed from wood to conserve strategic materials. Armament consisted of 24 unguided 73mm rockets in the nose. Only one manned test flight occurred on March 1, 1945. Lothar Sieber launched from a tower near Stettin am Kalten Markt. The canopy separated prematurely during ascent and the aircraft crashed, killing Sieber. No further manned flights were attempted before the war ended. Several unmanned tests demonstrated basic feasibility, but the Natter never approached operational status. The DFS-228 was a high-altitude reconnaissance aircraft designed for extreme performance at stratospheric heights. Development began in 1940 under the Deutsche Forschungsanstalt für Segelflug. The aircraft would be towed to altitude by a bomber, then use rocket power to reach operational height above 15,000 meters. The DFS-228 featured a pressurized cockpit, a necessity for flights above 12,000 meters. Wings were long and slender for efficient high-altitude flight. The Walter rocket motor provided brief bursts of thrust to reach maximum altitude, after which the aircraft would glide while conducting reconnaissance. Flight testing revealed significant challenges. Temperature extremes at altitude caused structural problems. The pressurization system proved unreliable. Several prototype crashes delayed the program. By 1945, the strategic situation had deteriorated too far for reconnaissance missions deep over enemy territory to remain viable. The DFS-228 never entered service. The Heinkel HE-176 was Germany's first liquid-fuel rocket aircraft. First flight occurred on June 20, 1939, making it one of the earliest rocket planes in history. The aircraft used a Walter RI-203 engine burning a mix of hydrogen peroxide and calcium permanganate. This propellant combination was less energetic than later formulations, but more stable. The HE-176 was purely experimental, intended to validate rocket propulsion concepts rather than serve operational purposes. The fuselage was compact and streamlined. The pilot sat in a prone position to reduce frontal area. Maximum speed reached approximately 750 kilometers per hour during test flights. Despite successful demonstrations, the Luftwaffe showed limited interest. The aircraft's endurance was measured in seconds rather than minutes. Range was negligible. The HE-176 contributed valuable data to later programs, but was abandoned by 1940 in favor of more practical designs. Japanese rocket aircraft. Japan pursued rocket propulsion primarily as a desperate last resort weapon during the final year of the war. Technical capability lagged behind Germany, and most Japanese designs were intended for suicide missions rather than reusable interception. The Mitsubishi J-8M Shusui was a direct copy of the Messerschmitt 163. Japan acquired plans and technical data through submarine transfer in 1944. Development proceeded under immense difficulty as American bombing disrupted industrial capacity and material shortages worsened. The Japanese version used a Toku Rho.2 rocket motor, a reverse-engineered copy of the German Walter engine. Propellant chemistry remained identical, with all the attendant handling dangers. Armament consisted of two 30mm Type 5 cannons. Only one powered test flight occurred. On July 7, 1945, the prototype crashed during landing approach, killing the pilot. Engine reliability problems plagued the program from the start. By August 1945, only a handful of airframes existed, none operationally ready. The Shusui contributed nothing to Japan's defense. The Mizuno Shinryu was a point defense interceptor designed for ramming attacks against B-29 bombers. The concept envisioned mass production of simple rocket-powered aircraft that would be launched vertically to intercept raids. Pilots would aim for the tail section of bombers, using the aircraft itself as a weapon. The Shinryu existed only as wooden mock-ups and design studies. Proposed propulsion used solid-fuel rockets for simplicity and rapid production. The fuselage would be constructed almost entirely from wood. No ejection system was planned. Pilots were expected to bail out manually after ramming, though survival seemed unlikely. Development never advanced beyond preliminary stages. The technical challenges of vertical launch, guidance, and structural integrity during ramming proved insurmountable with available resources. The Shinryu remained a paper project. Soviet rocket aircraft. The Soviet Union explored rocket propulsion primarily through experimental programs rather than operational deployment. Research focused on understanding German advances and developing indigenous capability for future applications. The Berezhnyak-Isaev BI-1 was the first Soviet rocket-powered aircraft. Development began in 1941 under extreme wartime pressure. The design used a liquid-fuel rocket motor developed by Alexei Isaev, burning kerosene and nitric acid. This propellant combination was less efficient than German formulations, but easier to manufacture and handle. The BI-1 first flew on May 15, 1942. Initial flights were unpowered glides to validate aerodynamics. Powered flights began in 1943. Performance included speeds approaching 800 kilometers per hour and climb rates that exceeded any contemporary fighter. Testing revealed severe stability problems at high speed. On March 27, 1943, the seventh prototype broke apart during a high-speed test run, killing pilot Grigory Bachivanji. Investigation revealed compressibility effects that early designers poorly understood. The BI-1 program was suspended pending further research. Several improved variants were studied. The BI-2 featured a more powerful engine and refined aerodynamics. The BI-6 explored ramjet propulsion in addition to rocket power. None progressed beyond prototype stage. By war's end, Soviet leadership concluded rocket fighters offered insufficient practical value compared to development costs. American rocket aircraft development. During the war, American rocket aircraft development focused on research rather than combat deployment. Programs emphasized understanding high-speed flight characteristics and validating technologies for future applications. The XP-79 was an experimental flying wing interceptor intended to destroy enemy aircraft through ramming. The concept emerged from Jack Northrop's fascination with tailless designs and the belief that heavily reinforced wings could survive collisions with bomber tails. Original plans specified rocket propulsion using an aerojet motor. Development delays and changing requirements led to substitution of two Westinghouse turbojet engines instead. The aircraft's unique feature was a prone pilot position, reducing frontal area and supposedly protecting the pilot during ramming attacks. The sole prototype crashed on its first flight, September 12, 1945, killing test pilot Harry Crosby. The aircraft entered an uncontrollable spin shortly after takeoff. No further development occurred. The XP-79 demonstrated the extreme difficulty of flying wing configurations without modern stability augmentation. The Ryan FR Fireball was a mixed-power fighter combining a piston engine with a supplementary rocket motor. Though not purely rocket-powered, it represented American exploration of rocket assistance for tactical aircraft. The design used a Wright R-1820 radial engine for cruise flight and a General Electric I-16 rocket for brief bursts of high speed during combat. Development began in 1943. The concept aimed to combine conventional endurance with rocket-assisted performance when needed. The rocket motor was mounted in the tail, fed by monoethyl aniline. Burn time was limited to approximately 6 minutes at full thrust. The FR-1 entered limited service with the Navy in 1945. Operational use was minimal before the war ended. Pilots found the mixed power concept awkward. The rocket motor added weight and complexity while providing only marginal performance improvement over pure turbojet designs already in development. Production ceased after fewer than 70 aircraft. The Bell XP-59 era Komet, while turbojet-powered rather than rocket-powered, influenced American thinking about reaction propulsion. It demonstrated that non-propeller aircraft could be practical, paving the way for post-war research aircraft like the Bell X-1. Technical challenges. Every rocket aircraft program faced fundamental problems that conventional designs did not. Propellant chemistry was universally dangerous. German T-Stoff and C-Stoff were hypergolic and corrosive. Soviet nitric acid destroyed seals and metal over time. Japanese attempts to manufacture Walter-type propellants resulted in numerous fatal accidents. Endurance limitations made operational planning nearly impossible. 7 to 10 minutes of powered flight meant pilots had no margin for error. Navigation had to be perfect. Target location had to be precise. Any miscalculation left the aircraft powerless and vulnerable. Landing characteristics were uniformly poor. Most designs landed unpowered at high speed. Conventional landing gear was often replaced with skids to save weight. Approach speeds left no room for correction. Accident rates during landing exceeded those of conventional fighters by orders of magnitude. High-speed flight introduced aerodynamic phenomena that designers poorly understood. Compressibility effects caused loss of control as aircraft approached the speed of sound. Shock waves formed over wings and control surfaces, rendering them ineffective. Several test pilots died before engineers grasped the physics involved. Conclusion: rocket aircraft represented the extreme edge of wartime innovation. They emerged from desperation, ambition, and the relentless pressure to find decisive advantages in aerial combat. Germany alone fielded operational rocket fighters, yet even the Me-163 achieved negligible impact despite its revolutionary performance. The technical lessons proved far more valuable than combat results. Understanding high-speed flight, hypergolic propellants, and pressurized cockpits laid foundations for post-war supersonic research. The X-series aircraft that broke the sound barrier descended directly from wartime rocket programs. Ballistic missiles borrowed propulsion systems developed for these fighters. These aircraft also revealed fundamental limits. Pure rocket propulsion could not sustain flight long enough for practical military missions. The future belonged to turbojets and eventually turbofans that combined reasonable endurance with jet performance. Rockets would find their true calling in missiles and spacecraft rather than piloted aircraft. The pilots who flew these machines displayed extraordinary courage. They strapped themselves into experimental aircraft filled with explosives, knowing survival rates were poor and combat effectiveness uncertain. Their sacrifice advanced human understanding of flight at speeds and altitudes previously unimaginable. The rocket aircraft of the Second World War stand as monuments to technical audacity and the human cost of pushing into the unknown.